Finishing off our discussion on elastic properties of materials or elasticity, let's look at a few examples. So consider now the following example. You have sample problem number 1. A weight is suspended from a steel wire of length 1 meter and cross-section area 1 millimeter squared. The ultimate strength of steel is given 400 times 10 to the 6th power Newton per meter squared. What is the maximum mass that the weight can have without breaking the wire? What is the resulting elongation of the wire? Young's modulus of steel is given 200 times 10 to the 6th power Newton per meter squared. So because of the weight of the suspended object, the steel wire will be stretched. Initially, it has a length of 1 meter, so let L naught be equal to 1 meter. The wire has a cross-section area of 1 millimeter squared, so let A be equal to 1 millimeter squared. Convert to meter squared, you have 1 times 10 to the negative 6 meter squared. The ultimate strength of steel is given. Let that be S. S is equal to 400 times 10 to the 6th power Newton per meter squared. Likewise, Young's modulus of steel is given. Let that be Y. Y is equal to 200 times 10 to the 6th power Newton per meter squared. With this information, we are being asked for the maximum mass that the weight can have without breaking the wire. And at this maximum mass, what is the resulting elongation of the wire? The wire will stretch because of stress. Stress is just equal to F over A. Maximum stress that the object, that the steel wire can have or experience without breaking is given by the ultimate strength. So let's set the stress to be equal to the ultimate strength. So F over A is equal to S. Transferring A to the other side, we have F is equal to A S. Now, the force producing the stress is basically due to the weight of the suspended object. So F is equal to mg. Maximum stress is S. That means F is also at maximum. Maximum weight of the suspended object is, so F is equal to mg. For maximum F, we set the mass to maximum. So F is equal to m maximum times g. Replacing F by M maximum G, we have M maximum G is equal to A S. We are looking for the maximum mass of the suspended weight. So isolating M max, we have AS over G. We know A, we know S, and we know G, 9.8 times 10 to 9.8 meters per second squared rather. We are able to calculate the maximum mass to be 40.816 kilograms. The maximum mass that the suspended weight can have without breaking the wire. Now, to determine the resulting elongation of the wire, this is elongation, length deformation, we use Young's modulus. Young's modulus is given by stress over strain, F over A divided by delta L over L naught. We are looking for the resulting elongation at maximum mass of the weight. At maximum mass of the suspended weight, stress is just equal to the ultimate strength, S. So we replace F over A by simply S. we have y is equal to S over delta L divided by L naught. Rearranging the equation, we have SL naught divided by delta L. We are looking for the elongation. We are looking for delta L. So isolating delta L, we have delta L is equal to SL naught over Y. Replacing the variables with the known values, we know S, we know L naught, and we know Y. We are able to determine the elongation. We are able to calculate delta L to be equal to 2.000 meters. Moving on to the next example, we have sample problem number 2. A bust is suspended from a spring with a force constant of 15 Newton per meter. The spring is stretched 5 centimeters. Determine the mass of the bust. So we have a bust suspended from a spring. The spring has a force constant or spring constant of 15 Newton per meter according to the problem. So let that be equal to K. Thus, as a result of the weight of the bust, the spring will be stretched. The spring is stretched 5 centimeters. Let that be Y. Y is equal to 5 centimeters. Convert to meters. Determine the mass of the bust. So again, the bust has mass. It has weight vertically downwards. Because of its weight, the spring will be stretched. The spring will react by producing spring force. It will produce F spring. These are the forces acting on the object, the weight and F spring. The bust is simply suspended. Static case, so we have equilibrium. F net is equal to 0. F net is summation of the forces acting on the object. Therefore, F net is just equal to weight plus F spring. Analyzing this using component method, looking at the diagram, we see that all the vectors are vertical, therefore no x component. We go to the y component of F net, we have F net y. Y component of 0 is 0. Y component of the weight is vertically downward, so negative direction. So minus W. F spring is vertically upwards, positive direction, so plus F spring. Weight magnitude is just mg, so we have minus mg. F spring, magnitude of the spring force is just given by kx, or in this case, ky. Minus mg plus ky is equal to 0. We are looking for the mass m of the bus. So isolating m is equal to ky over g. We know k, we know y, and we know g, 9.8 meters per second squared. Kompleto. We are able to calculate the mass of the bus to be 0.077 kilograms. And lastly, we have sample problem number 3. You have a spring of force constant 10 Newton per meter. It is compressed 5 centimeters using a 1 kilogram wooden block. The spring is released, sending the wooden block sliding along a level floor. Assuming a kinetic friction of 0.1 Newton, that is to say, between the wooden block and the level floor, there is friction, kinetic friction of 0.1 Newton. How long will the wooden block slide along the floor before coming to a stop. The problem tells us that the force constant or the spring constant of the spring is 10 Newton per meter. Let that be K. The spring is compressed 5 centimeters, so let that be X. X is equal to 5 centimeters. Convert to meters. The mass of the wooden block is 1 kilogram. Let that be M. And the kinetic friction of 0.1 Newton, let that be F sub K. F sub K magnitude is equal to 0.1 Newton. The motion of the wooden block is divided into two. First, you have the spring action. The spring applies force on the wooden block, pushing it, giving it an initial velocity. The next part is the wooden block slides on the floor with the initial velocity provided by the spring action. So first, let's look at the spring action part. The spring compressed and then released. The spring, using the energy stored in it, will perform work on the wooden block, giving it an initial speed. So using conservation of energy analysis, you have initial energy is equal to final energy. You have initial kinetic energy plus initial elastic potential energy is equal to kinetic energy final plus elastic potential energy final. Since we're talking about level floor, we can safely assume that the spring action is also done on the horizontal axis. So, initial gravitational potential energy is just equal to final gravitational potential energy. So, we can cancel out the gravitational potential energy, leaving us with only elastic potential energy. Likewise, the motion is just horizontal motion in a straight line. There's no rotational or angular motion, so no rotational kinetic energy, just linear kinetic energy. So again, initial kinetic energy plus initial elastic potential energy is equal to final kinetic energy plus final elastic potential energy. Initially, when the spring is released, the wooden block is at rest, so initial kinetic energy is 0. Initial speed of the wooden block is 0 as far as the spring action is concerned. And initially, the spring is compressed. It has elastic potential energy, 1/2 kx squared. In the final case, the spring imparts speed on the wooden block, so it has kinetic energy, final, 1/2 mv squared. And the spring now is uncompressed, it has been released, therefore, it is no longer compressed, it no longer has elastic potential energy. X is equal to 0, for instance. Elastic potential energy final is equal to 0. In other words, elastic potential energy initial is converted into kinetic energy final. Isolating V, V is equal to square root of kx squared over m. We know k, we know x, and we know m. Kumpleto, we are able to calculate the speed given by the spring action on the wooden block. V is equal to 0.158113883 meters per second. And it is this speed that becomes the initial speed for the sliding motion of the wooden block. After the spring performs work on the wooden block slides on the level floor. So, on the level floor, we have the following sliding motion. Initial velocity, say this is the level floor, this is the wooden block. Say the wooden block is now moving in the positive direction. The motion is in the positive direction. So initial velocity, V naught, has a magnitude equal to 0.158113883 meters per second, positive direction. And the problem tells us eventually the wooden block comes to a stop after sliding on the level floor. So final velocity is 0. To be able to calculate the time of travel, we need the acceleration of the wooden block. For that, we perform force analysis on the wooden block. The wooden block is on the level floor. The wooden block has mass m, therefore it has weight vertically downwards. The horizontal floor surface will produce normal force N, vertical, positive direction because the floor is horizontal. The wooden block is sliding along the floor. There is kinetic friction, as the problem tells us, kinetic friction of 0.1 Newton. Kinetic friction is always opposing the motion. Since we had assumed the motion to be positive direction, kinetic friction will be in the opposite direction. Kinetic friction will be horizontal, negative direction. From non-zero velocity, the object comes to a stop. Therefore, the object is decelerating. The acceleration is opposite in direction as the motion. Since there is acceleration, F net is equal to ma. We have an accelerating system. F net is summation of the forces acting on the system. Therefore, F net is equal to weight plus normal force plus friction. Using component method to analyze this vector equation, we have x component. F net x is equal to x component rather of A. A is horizontal, negative direction. Therefore, we have minus ma. Weight is vertical, no x component. The same goes for weight, no x component. Friction is horizontal, negative direction, so minus f sub k. Minus ma is equal to negative fk. Isolating a is equal to fk over m. We know fk, friction, kinetic, 0.1 Newton. We know m, 1 kilogram. Turns out we don't need to go to the y component. In x component, we are already able to calculate the acceleration of the wooden block. The acceleration magnitude of the wooden block is equal to kinetic friction magnitude divided by the mass of the wooden block. Plotting in the values, we are able to calculate that the acceleration magnitude is 0.1 meters per second squared. The diagram tells us that the acceleration is heading in the negative direction. Therefore, acceleration A vector, the negative direction must be added to the magnitude of the acceleration. Therefore, the acceleration, the vector acceleration is equal to negative 0.1 meters per second squared. You have an accelerating system, constant at acceleration A, constant at negative 0.1 meters per second squared. You have uniform acceleration. For uniform acceleration, you have 4 equations to choose from. 4 equations to analyze the motion of the object. One of those equations is V is equal to V naught plus A t. Final velocity is 0. The object comes to a stop. We know V naught. We have calculated A, the only unknown is T, so isolating the time of travel, T is equal to negative V naught over A. Plotting in the values, we are able to calculate the time of travel of the wooden block as it slides along the level floor. 1.581 seconds. And that's it for our discussion. That's it for this video. That's it for our discussion on the examples part. And that's it for our discussion on the elastic properties of materials. So thank you for watching.